All right, so we're about to start section 1.2. When I moved stuff around, I found two more graphs. So we also have the square root function and the cube root function. So the square root here, notice there's nothing to the left of 0. That's because we can't square root negatives. This is going to be one of our domain restrictions. The other one is our asymptotes. In 1 over x, if x equaled 0, 1 over 0 is undefined, unknown. So that is another location of a domain restriction. The third one we will see eventually is logarithms. You can't log 0 or a negative number. But before we dig into domain and range, let's talk about interval notation. So you need to be comfortable reading this, writing it, understanding it. So the book had two lovely tables. This one is an inequality. So we read that as x is greater than a. In interval notation, that's from a to infinity. If we graphed it, they put a parenthesis, or you could put an open circle, to infinity. And in words, x is greater than a, etc., etc. So notice on our equals, we're going to put brackets. Unequal is going to be parenthesis. So here's a little bit more, but the pictures have open circles and closed circles. This is what I grew up with. It's what I normally use. Open circle means we get really close, but we don't hit the number itself. Closed circle means we do actually get to include that number. And then the bolded arrow means it was from 10 and everything smaller. Or here, greater than or equal to 10 and everything bigger. Or here, it's just two arrows, so it's all real numbers. So there is a fancy symbol here. It's sometimes called like a double line R. You draw two verticals. And then you put the R like over both. That's how you would handwrite that particular R. That's how most people handwrite it. But that's the symbol for everything from negative infinity to positive infinity, because it's a little bit easier to write. Now, some of your calculus professors might get a little pissy if you write that instead of negative infinity to infinity, FYI. So just try to gauge what kind of professor they are. All right, so to practice that, here in figure 7, specify the graph set in A. We're going to describe this in words. Then we're going to do set builder notation, which is this middle one here. And it's going to look really similar to the inequality, except you put these, it's hard to see, but they're curly braces, and then H. Curly braces on the computer are to the right of the P. The normal button gives us brackets, and then the thing above that is what's called a curly brace, or just brace. All right, so words first. When we look at this graph, I see the bold arrow to the left, goes up to -2, and I got a closed dot. Between -2 and -1, kind of hard to see, but it's not filled in there. There's a gap. And then from -1 to 3, we get to include -1, but not 3. So let's try to say all that, just a little less wordy. Okay, so all the numbers smaller than -2, including -2, and all the numbers from -1, including -1, up to 3, not including 3. Very tedious, but mathematicians prefer to be specific, even if it sounds tedious. It is very clear. I am including the -2, I am including the -1, and I am not including the 3. So it looks a little repetitive to say it that way, but to say it mathematically, we would rather be redundant and clear than try to imply something by leaving words out to make it sound shorter or more English speaking. Mathematicians don't speak English, they speak math. Now, set builder notation. Should be able to put this here. So there's our curly brace. The set of all H, X, A, the letter you pick there doesn't matter. Then we put a vertical line, which on my keyboard to the right of the brackets braces button, there is the other slash and then the vertical line. That's called a pipe symbol because computer scientists are also weird. Feel free to look it up. It's an interesting etymology. It comes from a painting of a pipe that is not a pipe. Oh, philosophy. All right, so the set of all 8, we read that pipe as such that we have H is everything less than, and we need equal to, so I am going to underline that and then turn off the underline. -2 and then we have from -1 our H up to 3, and then I'm just going to go back and put the line here like so. And then we close the brace. Blech. So even the set builder notation, like it's smaller, but it's still a bit weird. Like it just doesn't get at, I just want you to list these numbers. If we use interval notation, then what I do is when it's an arrow all the way to the left or the right, I think of that as the value at infinity. So this one is going to go from -infinity. Now, -infinity itself is not a number, it's an idea. It's saying on into the negative numbers forever and ever. So it does not get a bracket because it is not somewhere we can arrive. So it gets a parenthesis. So from -infinity all the way up to -2, filled in circles, so we give it a bracket, a U to stick it together, another bracket, and then it goes from -1 to 3, and then we put a parenthesis on the 3 because we don't include the 3. So there is our interval notation symbolic way to say what the words in the set builder notation there say. So in mathematics, we usually use interval notation when we're answering a question about what values do a certain thing, like what values are in the domain. Then that's asking, like when it's asking for a set, a collection of values, we'll often use interval notation if those values are going to be numbers. All right. So domain and range. So the domain, we saw this earlier, is the set of all the input values. The range is the set of all the output values. One of the ways I remember it is domain comes before range in the alphabet, X comes before Y. So domain is all the X values, range is all the Y values. Some people also remember like range like a mountain range. Mountain ranges go up and down. So range is your vertical stuff. Domain, as far as the eye can see, it's my domain. It's a left-right thing. All right, so like I was mentioning earlier, our 2 common cases of domain restrictions are going to be square roots and dividing by a variable. The third one comes from logs. We cannot log 0 or negatives. Square root just can't be negative. And then dividing by something, the something we're dividing by cannot be 0. All right, so then we got a little how-to list. So we got a couple of functions here. So f of x, we're going to find the domain and range of, and then g of x, we're going to find the domain and range of. The range on these can be a lot more awkward, but we'll give it a shot. A lot of times on these, if it asks for the range, most of the time what it means is go graph it, see what the graph does, and then just come back and tell us. But this guy here, our first one, the domain at least. So my denominator, I'm dividing by something, so that something cannot be 0. That's my first restriction. So square root of x plus 3 cannot be 0. And then that square root is a square root. So we can't put negative numbers inside a square root. So we also have, so I'm going to put and x plus 3 is greater than or equal to 0. So this on the right here is because it's square root. Square root. This is because of the denominator. Both of these have to be true for our to be in our domain. So even though over here on the right, x plus 3 has an equal 0, the left is saying, no, it can't. So what we're actually going to end up with is just x plus 3 is greater than 0. We can solve that. But I want to be very clear why this is happening. And I think looking at two cases makes that a little clearer. All right, so the square root will not be 0 when the inside is not 0. And the inside is not 0 when x is negative 3. All right, and then over here, same thing. We just move the minus 3. So x is greater than or equal to negative 3. But x cannot be negative 3. So our domain is everything from negative 3 and bigger. So the set of all x such that x is strictly greater than negative 3. Or interval notation, we would say from negative 3 with a parenthesis to infinity with a parenthesis. All right, now square root functions are interesting because most of our functions, like, we tend to get everything for the range, unless there's a restriction, and then we might knock out one value. So if you look at like the range on the reciprocal function, x can't be 0 and y can't be 0. That's your domain and then your range restriction respectively. But the square root function starts at 0, 0 and graphs. So it's on the bottom here, but that still idea of it's going to start at a point and whoop, is going to hold true here. But because of the nature of this graph, the x plus 3 is actually creating a vertical asymptote, which means we have some asymptotal behavior. Let's see. If I can't sneak over to Desmos graphing calculator. Okay. So you're going to find on your writing assignments and stuff, it's going to ask you to graph, and you can absolutely use Desmos to help you get an idea of the sketch, but you would want to be able to produce that sketch yourself most often. All right, let me. Okay. So I typed this in the Desmos graphing calculator. This is what it got me. I zoomed out, graph is doing the same thing, except that -3 is producing that asymptotal behavior. So our range, though, because it's an asymptote, this will keep going down and down and down. And then for the top, it'll keep increasing and increasing and increasing. So the range for this is actually going to be all real numbers. There is not a good way to figure that out algebraically, though. Like, it's basically, I'd sit here and talk about what the graph is going to do, the range of each piece of it, and then poof, I'd write the answer. And that's really just like in my head, kind of picking numbers, plugging them in, thinking about what the graph's going to do based on those pieces. But at the end of the day, you can legit just graph it. But a question like this, not going to ask, like the first one, not going to ask you for a range on that. Domain, totally fair. Range, not a good test question. G of X here, though, you guys actually did this in college algebra, so you're responsible for remembering rational functions. Alrighty, so this guy here. Let me come over here and see if I can't get that to paste. Yay. All right. So domain and range of this one. So again, domain, we don't have a square root, no logs. All we have to worry about is dividing by 0. So x cubed minus 4x is not allowed to be 0. Which then begs the question, well, when is it 0? What makes that 0? So we need to solve this. Now I know some people will say, all right, I add the 4x over, I divide by x. Don't ever divide by x. And then you'd square root and you say 2. Okay, it can't be 2. And that is one of the numbers. There are actually 3 values we have to exclude here. So both of those things have an x. So when that you want to divide by x, rewind, put everything back on the same side, factor the x out. So that's our first step, is I pull the x out. I have x squared left, minus 4. This is not allowed to be 0. Now, the same way we split this when it's equal to 0, we can do the same for not equal to 0. So one of our values now is 0 itself. X is not allowed to be 0 for this particular graph. And then the other is x squared minus 4 is not allowed to be 0. So again, tempting, you can move the 4 over and square root, but remember, when you write the square root, you put the plus or minus. You would get 2 values if you use the square root property. But I find remembering that this factors is a little bit more useful of a skill. So we have x plus 2 cannot be 0, which means x cannot be -2. And x minus 2 cannot be 0, so this means x cannot be +2. So the domain in words is everything except 0, -2, and 2. So let me type that. So an interval notation, that's going to be a little more tedious. What I like to do for my interval notation is I actually draw a number line, sketch it in, and then I just use the number line to produce the intervals. That way everything's in order. It just seems to go a little better in my head that way. So there is our -2, there is our 0, there is our 2. And we're saying everything except, so that means open circles there, and then everything here, and here, and here, including both of our infinities. All right, so when we go to write this, the first interval is from negative infinity to -2. Then we have another one, so we stick a u. Our next one is from -2 to 0. And everything is parentheses here because we cannot include these values. Next one is 0 to 2. And finally, the last one is that 2 up to infinity. So that is what it will look like when you're saying everything except 3 numbers, 3 values. You end up with 4 intervals. Because you're saying everything before, between 2, between the other 2, and after the last one. All right, now the range. Come back over here. So the range on this guy involves figuring out what the horizontal asymptote is. And then we would see if it could still cross that value. And since we have so many intercepts here, and if we looked at the factored form, everything is singles. We don't have any doubles, so we have no x squared behavior. So it's all going to be opposites. So we're literally just checking, is it going to cross at that horizontal asymptote? Since the bottom is a higher degree, the horizontal asymptote is going to be y equals 0. So we're asking ourselves, is there a value that I can plug in that would give me y equals 0? So on the bottom here, like, we want to avoid our no-no numbers, but otherwise we don't really care what the bottom is, because if the top is 0, it should divide. So on the top, we have 3x equals 0. That's our, can we use this? Divide by 3, we get x equals 0. Can we have x be 0? So on top, yeah, I'd get 0, which is, what I was wanting. On the bottom, though, 0 cubed minus 4 times 0. So this graph is never going to cross the horizontal asymptote. So the horizontal asymptote is our only domain restriction. Every other value I can think of, there should be an x value that will produce it. So the range, if we do our number line, there's our 0. Everything before, everything after. So negative infinity to 0, stick it with a u, 0 to infinity. Whew, craziness. All right. Now this one's good practice, reading your graph, understanding what the graph is and is not saying. So this one is just asking the domain and range of this particular picture. So domain, remember, is x values. So I think of it like, I look at the x-axis because it's easier to read the numbers there, but I'm asking myself, so where does this graph have points? What's my smallest x value with a point? And -3, and then I got points, I got points, I got boop, and then I stop at 1. So my domain goes from -3 to 1. And now I just have to go back and ask myself, do I include these numbers or not? When I look at the -3, it's an open circle, so it gets the parenthesis. To say we can get really close, -2.9999999, but not -3. And up here at 1, it's a closed circle, so that's going to get a bracket to say, yes, we can actually use x equals 1. Now our range. Now we're looking at the vertical. So it can help here, like when I have a graph on the overhead or something and I'm gesturing at it, I'll put my hand like a horizontal line, and then I'll say, what's the lowest Y value? So when you're doing this, you're asking yourself, like, how low does it go? But think Y value, not the X value where the low point occurs, but what is the lowest it can go? So this guy, the low point is down here, and that low point is -4. And then our high point, see an open circle over here, but there's also there at, it looks like 0, 0. We're meant to assume that's 0, 0, and that it is indeed hitting 0 as a value. So the range numbers sweep from -4 up to 0. And the -4, like we can clearly see on the right, closed dot. So that's definitely a bracket. The 0, though, even though the open circle on the left, if this graph like didn't go all the way up, then we would have a parenthesis. But because this graph actually does hit the x-axis there in the middle, this 0 gets a bracket because there is a point on the graph that has 0 for a y value. So it must be included in the range. Now I know some people might look at this, well, how do you know it doesn't go to 0.1 on the y-axis? I don't. It's when you're looking at pictures like this, just assume it's whatever the closest tick mark is. And the closest y value tick mark is 0, so we assume that's 0. If they wanted it to be 0.1, they'd have to zoom in and put 0.1 as a tick mark. All right. And then the last thing we have, and the book has a different example, feel free to look at that. The classic example is the absolute value. But we have what's called a piecewise function. We are not going to use these that often, but they pop up in calculus right at the beginning because they use this to talk about limits a whole bunch. So a piecewise function is a function in which more than one formula is used to define the output. Each formula has its own domain, and the domain of the function is the union of all of these smaller domains. We notate this idea like this: f of x equals formula 1 if x is in domain 1, blah, blah, blah. So classic example, the absolute value function, we can write it as a piecewise function. We say the absolute value of x is going to give us whatever x is if x is greater than or equal to 0. So when x is positive or when x is 0, we get that number out. If x is less than 0, if x is negative, then our output is going to be the opposite of x, meaning the opposite of a negative would be positive. So it'll give us back the positive number that we expect with absolute value. So when you're doing piecewise, like you're taking each graph and then you look at whatever the domain they tell you is, and you erase whatever parts aren't in that domain. Now on physical graph paper, that can still look really ugly. So it can be helpful to actually like put the domain restrictions first and then think about, all right, what's this graph look like just in here? Let me just sketch there and not put marks somewhere else. So here we go. We have when x is less than -1, we are going to have the graph of x cubed. When x is between -1 and 4, we're just going to be the value -2. So that'll be a flat line, a constant. And then if x is greater than 4, we're going to be doing the square root of x. All right. All right. So I'm just going to sketch in here -1. I don't want to use a dashed line that looks like an asymptote, so how about instead I'm going to highlight, like, there's our first regional boundary, and then way over here at 4 is our second regional boundary, which means I'm going to need some slightly bigger numbers. Okay. So the first part of our graph, if x is less than -1, so to the left of our first, in our first region, we're going to have the graph of x cubed. So whenever you're graphing a piecewise function, one of the things you want to ask yourself is, what's the value on the boundary? Whether it's actually going to equal that or not, I need to know where that dot goes. So if x equaled -1, -1 cubed would be -1. So at -1, -1, I have an open circle. Then to the left of that, I'll keep graphing. So the next left value is -2. -2 cubed is -8. All right, so this guy goes way down pretty quick. So there's our first stretch. And we're going to leave it an open circle because that didn't have the equal bar there. Now my next one, the function is going to be -2 itself if x is close to -1. All right, so over here, another open circle, because there's no equal bars, and open circle. And then we just draw a reasonably straight horizontal line between the two. So there's our middle stretch, just that flat line. Now our last piece is that square root function. So it says just for when x is bigger than 4, but I need to know, where does this open circle go at 4? Square root of 4 is 2. There's no negative in front of the square roots. That means it is +2. We only worry about the plus or minus if we write the square root. Here, the book wrote the square root. They didn't put a minus in front of it, so it must be the positive root. So at 4, +2, there is our square root. And then, like if we were over at 9, 9 would go up to 3, so this one's gonna shoot kind of like that. And that is how you graph a piecewise function. Figure out your boundary points, and a lot of times it's like, figure out the direction the graph will go. In calculus, you'll learn other ways to figure out, like, does it turn around somewhere? And then you can graph those points as well. But usually when you're talking about piecewise functions, what you're actually looking at is, how can I make it match? So my middle line segment here, like the values aren't lining up at all. But if I could change that middle line segment, what would I have to change it to so I could make those endpoints line up? It's just some food for thought, but there is the end of 1.2 for you. Again, any questions you have from the video, write them down, email me, group me, or bring them to class. Class would be best so everyone can benefit. Yeah. And don't forget the writing assignment.